Starting now. All right, it's another draft physics video presentation. I'm here with Franklin Hu, and I'm also here. It's just you can't see me yet. There, I'm here now, and we're going to discuss physics. Probably just from the elemental. Physics has given us this whole big story. And frankly, they don't have evidence for it. It's a very weakly evidenced story of reality. The orbiting atom stuff, bent space is an answer, virtual photons. I would even say silly ideas like entanglement, like the elemental processes are more sophisticated than these complex biological machines. And if there was such a thing as entanglement, the biological organism would have already capitalized on it, and we'd be, controlling each other. But anyway, that's all. That's in one of the subjects. Could be in the range. Of late, we've been discussing photons and their structure, and so we'll probably spend some time on that. Franklin has a website where he has a theory of everything. I think it's completely wrong, but so we probably both share some opinions like that. I mean, it's completely right in the sense that it's simpler and it's mechanical. I'd argue it's not enough. It doesn't get simple enough in the sense of, I keep arguing about this idea that push is the elemental concept. Push is easy to understand. Pulls are impossible to understand. So maybe we can talk a little bit about that. Like, there's no real elemental pull. And that's where you have to start inventing woo, really, is when you start saying something says, come to me. Well, how does it exactly say that? When get the hell away from me is easy. You throw something at the guy and he knows, get the hell away from me. So I'd argue that that's where physics should have started. He might say it should have started someplace else, but that was where their first big mistake was to think pull was really possible. And that's where it all started going the wrong way. Because they didn't understand it's all downhill, kind of a thing. So, hey, Franklin, anything you'd like to add? FranklinWho.com is the website.
Yeah, check out my theory. It's been out there for like the better part of 17 years, apparently, since 2003. Mad scientist scene since 2003. Yeah, actually, I would agree with most everything that you just said there. The mainstream is all really kind of don't have the answers, really. I mean, how seriously can we take these people when they can't explain, like, how charge works, how magnetism works, or how gravity works? I mean, basically all the attractive forces, they, still basically have no clue.
Well, even the idea of force brings something up to me, right? So little things that I say are like little trigger words, okay? So we let Maxwell decide that everything's electromagnetic, and so everything is the speed of light, when what we should have been saying the whole time was the speed of force, because all the forces move the speed of light. So everything that's a force, in the sense of one of these invisible things that's making something happen, they're all going the same speed. So why isn't it the speed of force, not just the speed of light? Light is just a category. Light is just one of the variations of the force, I would argue, not anything essential.
What exactly do you mean by force?
Force, I would cut the universe into two parts. The material bits are the electrons and protons, the heavy stuff. Okay, they don't do anything on their own. They have to be pushed anywhere they're going to go. And the other stuff is the force. And it's in little bits, little quanta, if we were to give a wave analogy or an ether analogy, the analogy would be is they are one of the wave fronts. I would say it's one little corpuscle moving in a straight line, where maybe you would argue that's a wavefront moving in a direction. But regardless, I would say it's a quanta of a little bit. It's a little grain of sand, and there's big balloons. Little grains of sand are hitting the big balloons.
The concept of energy? So let's say you have, a bullet flying through space. So generally speaking, I would say that it takes force to get that bullet, moving. That's what I would call force. I would call force like a particle that's, I don't know, associated with the bullet. Or...
No, I'm just saying there's only one thing moving in the universe, and that's this stuff called force, and it's going the speed of light. So there's no other speed, and the only thing it's doing is pushing. Okay, matter. Matter gets pushed where it's going. So, for example, the electron and the proton, we can't make a gun that shoots them like bullets. I can't shoot an electron to the moon. Can't shoot an electron to Venus. It won't get there. It won't go. It will stop. It'll get dragged.
Shoot an electron from the back of the electron gun to the front of the CRT screen.
I know, but that's exactly the point. You're doing that because you're shooting a bunch of X-rays behind it. Okay, so you're shooting a bunch of energy out of a heated element, and you're shooting ions. You know, the same gun is used to make protons fly, as is used to make electrons fly, as it is to make X-rays, to make gamma rays. It's all the same gun, exactly the same gun. So this gun is already shooting a bunch of photonic radiation. You know, they have to have big shields at a linear accelerator. You have to have big radioactive, you know, they have to put lead, you know, on the other side of the target. So when they go to, you know, work on it or something, they don't get irradiated by all the X-rays. I mean, there's a ton of X-rays in that beam. It's not just a beam.
I just want to get back to what you mean by force. I mean, I don't want to get into one of these arguments where we're arguing about definitions, because you're kind of using force in kind of an unfamiliar kind of way, like it's like
I'm saying the force is made of something. It's soldiers. It's not a field. Okay, there's no fields until the soldiers show up and make the field. So the force is actual particles. There's actual little tiny, discrete tiny particles that are moving the speed of light, and they impose force when they hit an electron or proton. They tell it to move.
Okay, well, I guess I would have to disagree there. I'm kind of a student of Newtonian mechanics, and my spiel is that I like to explain everything as you could explain it on, say, a billiard table, right?
Well, that's exactly what I'm saying, though. I'm saying, I'm giving you a pretty simple analogy. I'm saying the balls are hollow, the matter. Electrons and protons have no motion on their own. And you're creating a field of little balls that are in a confined space, okay, a box. If I put a bunch of BBs in a box, and they never lose their speed, right? They just bounce off the sides and they maintain their speed. And I put two objects in that box, the two objects will move right into each other, just like gravity, all right? Because they will, in fact, shield each other from the force. They'll shadow each other, essentially, and they'll move right into each other. So if I tell you that's a real thing, it's called mock gravity. It's a real thing. It's a, you know, that's a fact. So that's all you.
Maybe the analogy would be: I take my billiard table, I put my billiard balls on it, I put a cover on it, and I fill it with billion bees. And you're saying that if I see any movement of the balls in there, it's because the bees are pushing them around.
Exactly.
Is that
right? So I'm saying if you could make a three-dimensional box, fill it with BBs that never stop moving, and you put two billiard balls, you could suspend them in the box and they didn't fall because of gravity or any of that bullshit. I'm just saying they would end up moving right towards each other because the BBs would do it automatically. Because they'd get hit more on the outside than they get on the inside, and therefore they'd move into each other. So I'm just saying that that's the force I'm trying to talk about. All the forces are just little bits that hit something and make it move. And electrons and protons move much slower than, you know, the force is moving. And whatever movement they have because they're being forced to move.
Okay, well, I guess I would have to disagree then, because I don't believe that little force. I'll call them bees.
All right. Well, your alternative theory is, okay, there's a bunch of this gooey ether made out of positrons and electrons, really big things by comparison to the force, I would argue. That somehow they move in straight lines, and I can pick any straight line in the universe and they'll travel that straight line, but they won't. You can't make straight lines out of that grid. Okay, I can't make a checkerboard where it's equidistant from a center point. I can't make it circular. I can't make a circular geometry of discrete objects of ether that would create straight lines that are with the same length. So then everything would have an inconsistent speed because things would be traveling different distances, technically. So, I mean,
I've kind of been dealing with that exact kind of same argument about the nature of the ether. So, I mean, the argument is that if space is filled with like all these little whatever things, little particles, then say if an electron is shot through them, then, you know, it's going to bounce around and it's going to just do the whole Brownian motion thing. had a recent doing a recent argument about that whole thing. So I mean that's why that's the argument that there can't be ether. There's various arguments that if there was such thing, then it would obviously impede the forward motion of anything.
Well, that's what it does, though. I guess that's sort of what the foundational argument here is. This drag argument's a really valuable argument because, in a sense, we see that the elemental bits are dragged. You can't shoot an electron to the moon. Okay, why can't we? Why can't we shoot an electron a mile?
I don't know. I mean, maybe we can.
I'm just saying. I'm saying there's no experiment where they've been able to do it. So I'm just saying there's no experiment where you don't provide a continuous source of pushing energy. That is some sort of cathode ray instrument. Okay, where you have a charge differential and you're sending the electron through the charge differential. Without a charge differential, okay, without some mechanism to keep pushing it, it stops moving. I mean, accelerators have to... The reason why accelerators use so much electricity is because they have to keep pushing the electrons. They have to push them harder and harder and harder. Now, they have to keep creating a potential difference for the jump, for the jump, for the jump. They have to keep pushing them to keep them going. They won't just keep going all by themselves. You can't just trap them in a bottle, have them going around in a magnetic field, an even magnetic field, and just spin around and keep going. They won't go. They won't do it. They'll run out of gas.
I'm not so sure about that.
Well, I'm just saying I found no experiment where the electrons last any longer than you have a hot emitter. As soon as you turn the emitter off, there's no more electrons moving.
Well, I mean, then I can bring up an experimental result that contradicts that.
Well, good.
Which is that we do have superconducting.
Let's. Okay. Well, superconducting isn't moving electrons in the same way as I'm talking free electrons in space. So we're not talking about superconducting electrons. We're talking about moving electrons. We're talking about moving electrons through something like empty space, whatever the closest we can come to that is. We're talking about taking an electron moving from point A to point B in what we would presume to be empty space.
But the superconducting case would seem to be the worst case, where it's like, not only is it not empty, but there's like solid, like...
I know, but you've taken all the noise out. You've taken all the noise out. So the great thing about superconductors is if you've eliminated all the vibration of all of the electrons and protons, which means the geometry now isn't getting all screwed up by the noise. Heat is always a problem for electricity. Electricity hates heat. The hotter it gets, the more the electricity fails to get through a wire. So, I mean, it's already a known fact that you want to create resistance to electricity, make things hot, and you'll create resistance. So, obviously, the colder you can make it.
Still an example of electron...
I'm talking about electrons. I'm talking about electrons not moving through a conductor, okay? That's a medium. I'm not talking about electrons being conveyed from atom to atom. I'm talking about an electron moving freely through space. Like if I throw a wrench, I can hit Mars with it. I can actually throw a wrench from the space shuttle and theoretically hit Mars. I can't do it with an electron.
Well, that may or may not be true, but let's talk about wrenches. I mean, that's an interesting case. Yeah, you can throw a wrench, and if you throw it at Mars, it'll hit it, right? Theoretically.
Right.
But Newton's thing about...
I know, but there was...
once in motion, stays in motion, right?
Yeah, well,
my own question is, why is that? Now, what we're getting back to the ether thing is that, people are saying, well, that wouldn't be true if we had the ether because the wrench would run into all these ether particles and it would necessarily have to slow it down. But that experimentally, that is not what we observe. That to our experimental amount of error, which there might be, but generally speaking, it seems to be true.
But you can create you could create a device, in my opinion. Okay, I've already posed it. Where we know that helium atoms will travel through space. They'll shoot off of a star billions of light years away, and they'll arrive at the Earth's atmosphere. So we know that helium nucleuses can be shot to the moon. Helium nucleuses can be shot all over space. I can shoot them all over the place, and they'll actually get where I shot them. Electrons and protons don't. So what's the difference? Well, the difference is that the helium nucleus is complex enough that it creates an engine against drag. So my argument to you is that yes, electrons and protons are in fact dragged to a halt. They are stopped. Okay, and the fact is that the helium nucleus isn't, because the helium nucleus becomes more energetic the more you compress it. So the more pressure you push it into, the more pressure it pushes back with. So therefore, the wrench is really realigning a bunch of nuclear bits inside of the atoms, and it's compressing them, and by compressing them, they're more energetic and keep the wrench moving.
Well, I actually never heard of that argument that you couldn't send say a proton from here to the moon and it would just keep on going due to inertia. I would just presume that, because
well, let's just go back to the 50s. Let's go
that law.
Well, let's go
but
back
to saying that electrons don't obey that law.
I'm just saying that you've seen experiments with electrons. So let's say have you ever seen the experiment where they detect the mass of the electron by having it go in a circle? Okay, they have the electron move in a circle. They put two magnetic coils in to create an even magnetic field, that basically just confines the electron into a circle. And so the electrons are going in a circle. All right, so they have an experiment like that. Now the point is that that device, as soon as you turn the light bulb off, as soon as you turn the source off, the electrons stop. Okay, so they don't just stay in the bottle. They don't just, we can't create a bottle to trap them in. Now, theoretically, the magnetic field is frictionless. It's just like the gravitational field for the Earth. It's not dragging the Earth to a halt. So, that can't be, you can't say the electrons are stopping because of friction. So why do the electrons run out of gas? And look, you can see it even with radioactive material. The electron shoots off 3 inches, and that's as far as it goes, right? They don't go any further than 3 inches. That's how far an electron goes when it comes up.
It runs into stuff, I guess.
Well, I know, but it's smaller. It's smaller than all this other stuff. So how does an alpha particle, which is huge, how does that get anywhere, right? That keeps going. So the alpha particle keeps going, and yet the electron fails to keep going? That doesn't make any sense.
I would actually need to see an experiment showing that, because I would be kind of surprised if that were... In fact,
I can't show you the non-existence of the experiment they can't do. So, all I can tell you is you won't find an experiment where an electron actually travels any great deal of distance, okay, without perpetually being pushed. That is, without you increasing some electric potential that it's jumping across. So unless you keep re-energizing its electrical potential, it will not keep going. A linear accelerator depends on it, okay? A linear accelerator doesn't just accelerate it once and say, there, the electron went and we hit a target, 500 yards away. No, a linear accelerator has to keep accelerating the electron. It has to keep putting it over a charge potential. The whole trip is just a redoing.
Well, I should ask the Stanford linear accelerator guys, is that if you turn off all the accelerator elements in your linear accelerator, will that electron still, hit the target with some lower amount of energy?
Well, it's a pulse. It's a pulse laser.
It won't make it to the end.
It's linear, so it's not a circle. So it's a poor example because it's a pulsed laser essentially. A linear accelerator is basically a pulse of energy that shoots an initial collection of electrons, and then you keep pushing them along the path. So I can't, of course, the initial burst is enough energy to keep the electron going for some distance, but the point is they have to keep on accelerating it. They can't just accelerate it once. They have to accelerate twice and 3 times to keep adding speed. They can't.
Yeah, they add speed, but I'm just saying that I'm not convinced that electron wouldn't have inertia, wouldn't keep going, wouldn't go to the moon.
I'm just saying the bottle experiment sort of proves it.
Although I don't have any particular evidence to say that I haven't.
I'm just saying you don't see in a museum something like, well, here's an electron we trapped 50 years ago and he's still going around in a circle. There's no experiment where we kept the electron in the bottle, where we kept it going around and around. So I'm just saying that that's part of the evidence, and the other part of the evidence is they're not making electron guns to shoot down airplanes or electron guns to do anything else because they're totally ineffective.
Okay, well let's move on. I don't know that that really makes any big difference in either of our physics.
I think it makes a huge difference. So that's where we totally disagree. You don't understand the force concept, and so I'm basically telling you, well, the force is a real thing, okay, and it really does create drag, and so it's so fundamental to understanding what the difference between matter and what the difference is between force and matter, charge and the elements of charge. Charge is caused by something. It's not just something that magically happens. Something really has to move through space from one object to another object to say, get the fuck away from me or come near me. I mean, a real event.
Get back to your idea of force, which I disagree with. So, I mean, that's an interesting idea that force is this like this little particle and it's responsible for pushing everything around. And so I have to come up with some alternative to that to explain what's going on. And so, now what I say, what happens is that you have two particles and they go at some velocity. So Newtonian mechanics says, force equals mass times acceleration. And that's what force is typically given as, right? It's an amount of energy given to some.
Well, that's the amount it takes
to some velocity.
But that's the amount of energy it takes to actually hit it and move it. So every object is made of a different density, so obviously its acceleration is different. I mean, it's a lot harder to accelerate some objects than other objects because they have no density, okay? The more transparent they are. If I make a transparent sail on my on my sailboat, if I make a sail out of a bunch of, with a bunch of holes in it, my sail doesn't catch as much wind, So, I mean, that's all that's really saying is how much does an object catch of force? Acceleration is how much you catch.
The definition, more standard mainstream definition of force is, more tied up with that equation than being, say, a particle.
Well, I'm just trying to get to the point of understanding the distinction between the two things in the universe. There's stuff moving the speed of light. You can see that stuff is completely different than the matter stuff. That's all I'm looking for from you. Do you understand? I mean, there's stuff moving the speed of light. We can see that it takes time for the stuff to go from one point to another point, sort of indicating it's got to be stuff, whether it's ether, whether it's perturbation, whatever you want to call it. Something has to go from one place to another to interact with an electron and a proton. And moving electrons and protons is everything about matter theory. That's all that matters, is did you move an electron? That's an event. Moving matter with force is the only thing that's the event in the universe. If I was to say if we were to say what's the most important event in the universe, the event I would argue is force interacts with electrons and protons, and the electrons and protons change their position. That's the most elemental, fundamental mechanism in the universe. Could you agree with that?
Well, I just think it works differently. So, for example, I fill my, universe full of this, I call them positive electrons. You can call them anything you want. There could be neutrons, whatever. And I would agree that force does travel at the speed of light, and that's governed by the amount of how fast one particle can collide and affect another particle next to it, basically. So
right. Well, so you're just saying it's dominoes, right? You're saying basically it's a universe of dominoes, right? Let's just call them dominoes.
Much,
okay. Well, I'm just saying. Let's just say, and all I'm saying that's different than that. So I'm not saying anything fundamentally different, except I'm just saying, look, I can flick the domino. I don't need to bother hitting domino, 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 domino. I'm taking a certain thing, the domino, and I'm just moving at the speed of light. So I'm not bothering with all the dominoes having to interact with each other. I'm just going to flick them. So let's just say, let's agree to disagree. You say you need all the dominoes. I'm just saying, let's just pretend for the sake of argument that we get exactly the same outcome. A domino goes from point A to point B. So in my theory, it's one domino goes from point A to point B. In your theory, one domino hits a bunch of other dominoes, and then one domino hits point B, right? So we could agree that it's one little tiny spot that gets hit, one domino moves, right, of the ether, and that's the event, getting hit with a domino. And so,
and it's significant as to whether it's just one domino moving from point A to point B, or whether it is all the little dominoes in between. I mean, there's a pretty big difference between those two views, right?
I don't see how it's relevant at all. If that's a ghost, it doesn't matter. we're not seeing that part. We're saying the cause and the effect are the same ends, are the same exact ends. So whether it's Rube Goldberg and I have a duck hit a goose and the goose squeaks and then that hits a mouse trap and that does the, who cares what the Rube Goldberg is? We both have the same thing in the beginning. We have a boot that kicks and then we have a boot that kicks. So let's just concede that if the beginning is at the speed of light, we have a boot kick at the speed of light. And then we at point B, we have a boot kick at the speed of light. So if we could just agree that that's the end result, that a force basically is defined as a boot moves at point A, and then a boot moves at point B based on distance at the speed of light.
Well, the difference is that there is a big difference. And let me see if I can try to explain. Because in physics, we're trying to figure out, what the truth of the matter is. Now, it's true that either scenario pretty much ends up the same, pretty much. But logically, it can't be both of them at the same time.
I'm not saying it should be. I'm just saying it's an argument we're not going to solve because neither one of us has the magnifying glass that can see if the ether exists or the ether doesn't exist. I'm just saying I don't need one to create exactly the same from point A to point B consequence. And I'm saying the universe is basically, we could argue straight lines. I would argue that no force travels any curved line ever. Okay, it's always an least line. It's always this and down and that way or that way. A photon only moves in a straight line. All the electromagnetic radiation, all gravity, all everything is straight line vectors. That's what Maxwell's math shows overtly. Straight lines all over the place. They work great. So all the curved lines are created like a spirograph out of straight line geometry. And so all you're doing is making a curved line by combining two straight lines. So gravity would be the same thing. Gravity is a straight line from the outside to the center of the Earth. And the velocity of the moon, let's say, is a straight line. And those two straight lines intersect. And at every millisecond of the universe, there's being a bending of that line. But it's really an least line. It's really a bunch of little straight lines. It's not really anything called a curved path.
Well, let me see if I can argue for why I think all the dominoes exist. And I think that one of those possible reasons is that we could possibly experimentally find all those dominoes. Now, I know mainstream doesn't want to do that, but, I mean, we do have evidence that, say, in pair production, that we can get electrons and positrons to pop out of seemingly empty space.
I don't concede any of those things as being anything like a real experiment. So I don't think there's any such thing as pair production. But I'll give you an illustration of what I would consider to be what they're misunderstanding as pair production. If I move towards this camera, right? If I move towards the camera,
I don't want to get into an argument about whether pair production works. I'm just trying to get down to the argument that if space is filled with these positrons, electrons, as I hypothesize, that's my hypothesis, that then you should be able to find them. And the existing experiments are all kind of pointing to, even mainstream says that, space is filled with virtual positrons and electrons. It's responsible for the Lamb shift. Whenever we climb,
well, how could they even be arranged? Positrons and electrons. See, this is where we get back to fundamental theory, because see, I'm saying there's only two kinds of matter, electrons and protons, and it's charged. A neutron is just an electron and a proton. And charge is the fundamental feature here, okay? The fact that the two things have an opposite charge.
What is a positron in your theory?
There is no positron. I mean, there's a proton, okay? You want to call the proton a positron? I don't really care.
No, I mean, those are two distinct experimental things. I mean, they have definitely very different mass.
Well, I know, but I'm just saying that you don't believe that Rutherford's experiment is valid. Why do you think the positron experiment is valid? The first four guys who did the experiment said it's just a proton moving faster. Okay, so they didn't make news. There was no headlines. They just said, no, it's a proton. And then the guy who said, no, it's a new particle, it's a positron. He made the headlines. Same exact experiment, same exact results, completely different interpretation of the same experiment. So I'm just saying the experiment is weak. It's weak evidence of a new particle. And what is its function? What is its function in an what's its function in an atom? What is a positron doing? We know what the electron and the proton are doing. What the hell is the positron doing? Where's its hiding?
Now, I think the evidence for the positron is very strong because of the way we measure the masses of the various atomic particles. I mean, we can tell a difference between hydrogen and helium, and we can tell a difference between a proton and a positron by the amount of deflection that occurs in a fixed magnetic field. And a proton has much less deflection. This is how we measure mass. Proton is definitely 1,836 times more massive than a positron. So we definitely would not.
I read your paper. I read your own paper. You cast doubt on those experiments, and now you're telling me you think that's proven physics.
No, I'm casting doubt on shooting alpha particles at gold sheets and trying to make some kind of conclusion out of that.
Well, how do you think they measure? They can't measure the mass of the proton with any kind of reliability. The numbers change every frickin' year. They change the number. I mean, and how do you measure the mass? Just let me ask you the question. How do you measure the mass of a charged particle anyway? Every bit of atomic structure that you would make a scale out of is charged. There's electrons on the outside of atoms, protons on the inside. How can you possibly ever measure the mass of a proton? You can't do it without introducing a charge.
By you shoot it through a magnetic field. We know by Lorentz force law that that is going to exert a certain amount of force. We can see how much it curves.
Right, but that's its charge. That's its charge you're measuring.
Yeah, you're measuring and you're measuring the force. You have the charge. You have the magnetic field, and depending, the only thing that could possibly differ there is the mass.
All right,
so it's more massive, it deflects less.
Well, let's get to see. I would argue that most of these experiments are bullshit, just because it's like Stern-Gerlach. It's silver atoms. Okay, you tell me how much an ion weighs might be what you're doing. You're measuring how heavy ions are, but I don't think they're actually measuring protons. But whatever. Let's just say, for the sake of argument, I don't really care if the proton weighs more. All right, I know that its charge profile is exactly the same as the electron. That is, they're both as point sources. If I both reduce them to point sources, they create the same amount of charge. So whether I make the Earth bigger, I could make the Earth twice as big out of the same mass, and it doesn't change the gravity the moon sees. The moon would see exactly the same amount of gravity. So it doesn't matter how big I make something. I can make it any size, and its mass profile is still going to be the same. Okay, so it doesn't change anything. I can say protons are just bigger or electrons are bigger, right? If I made electrons bigger, in theory, they would be like helium balloons. They'd be lighter, right? So they'd move freely easier because they're getting hit by more force, right? They collect more of it.
Probably an easy, because, we both agree that we should go and look at the experimental evidence. And, so I would challenge you, if you think that the evidence for positrons as being different from protons is invalid.
I think it's weak. I just don't think there is any. I'm just saying that all they have is that the particle spirals.
There is. I would.
No, it spirals. I have looked it up. Okay,
Jesus. You would find experiments.
No, there aren't.
Just look at how do they measure the mass difference between even a proton and an electron. We measure.
How do you even create a positron gun? Okay, there's no such thing as positrons. You can't shoot them anywhere. They can't make any positrons. There's no such.
Well, yes, they do.
Where?
They definitely have in CERN. We definitely have positron beams.
You trust CERN. Okay, there's where I'll draw my line and say, no, there's no Higgs boson. It's bullshit. Okay, they never shot a beam of positrons. They never showed me every one of the little bits cycling to its death exactly like an electron, except with reverse polarity. They never did that.
You can see that in just a very basic cloud chamber
And again, you don't see it. You see, it's a rare event. It's a rare event. It's a very rare event. And so it's just, you could say, if the proton actually did get through the material without hitting anything, that is, without ever slowing down, then it would look like that because it was going faster. So that's all you have to do is change the speed. You change the speed, you change how tight or small the rotational depth will be. But okay, let's go back to photons. Okay, because I know this argument, you know, we've already started, and maybe we can make some progress. Okay, now we agree that there's polarization. Now I would point out, okay, that the polarization is gigantic. Okay, when you think about how it's thousands of atoms worth of polarization, right? The wavelength of light is, say, 500 nanometers. The average atom is 0.5 nanometers. So that means it's at least 1,000 atoms worth of polarization. And we're supposed to believe, okay, that a photon, whatever that is, this big giant thing, thousands of atoms big in its polarization, right? It's thousands of atoms of height. And it's going to interact.
Well, I'm not sure if I've heard that particular argument, but, you know, I'm not totally opposed to it, but I don't know that polarization is, you know, big.
It's completely, polarization is the same as antenna polarization. It's exactly proportional to the wavelength. So whatever the wavelength is, the polarization is that high. So it's true for like microwave antennas. You only need a 3-centimeter antenna for microwaves. Okay, because that's how long it takes electricity to get from one end to the other end. And so, you know, in terms of the timing of a pulse. So the only usable part of the antenna is the 3 centimeters, because that's the wavelength of the microwave. So the wavelength and the polarization are completely proportional, and they really have to do.
I'm not entirely sure about that. I mean, recently I saw a reasonable cutaway of what's inside of one of those antenna LNBs, right? Because I was wondering because it didn't seem to be very much inside of those things, and all that's inside of them is like this tiny little rod, which is, one of them is pointing this way and the other one's pointing 90 degrees that way, and you know, it's literally like only 2 centimeters long.
Right. Well, didn't I just say that, though? That's what a microwave is, 3 centimeters. So I'm just saying, I mean, it depends on the wavelength, right? So we're getting kind of.
You said 3 centimeters. I thought you meant, well, millimeters, actually, not centimeters.
Well, I know, but that would have to be dependent on what frequency you're using. So obviously, if you go from 10 gigahertz to 30 gigahertz, you know, you're changing the size of gets smaller and smaller. So the higher the gigahertz goes, you're 3 times smaller, 10 times 3. So you're talking 3 millimeters instead of 3 centimeters. You know.
It would, but that's and something in the C-band for satellite reception. I'm not exactly sure what the size is.
Well, the frequency is, yeah, right. So I'm just saying the higher the.
In any case, so what is your argument that?
Well, I'm saying the electron. I'm saying the electron.
Microscopically large.
Electron is 1,000,000 times, and I'm being generous, right? It's really 1,000,000,000 times or more smaller than the polarization of the light. So my argument is how does this thing that's 1,000,000 times bigger than this electron, how does this thing bounce off of that or interact with that? It can't possibly. So this must have components, in my opinion, right? The components of this can interact with this. One piece of this photon can interact with this, but not the whole photon. So when we see a photon, it does have to be produced by an antenna of atoms. More than one atom has to produce the thing that becomes the photon. So if you watch some of my recent videos, I've completely debunked the 2-slit experiment, explained how it's all just scatter, and you can explain the mathematics exactly. And because the photon really is a composite object. It's a timed event. It's an event that happens over a period of time. It takes time to make a photon because it's one piece at a time. One wave front, if I have to use waves, one wave front at a time has to be produced. And when it's received, the same thing happens. One wave front at a time is received. And my point, the polarization means that the waves are actually, if I have to call them waves, I would say the quanta, are actually just in different positions. So they fill the space. So one's here, one's here, one's here.
Well, if you had just like a solitary hydrogen atom, and you're just hitting that with energy, you know, would that be able to create photons in your, or polarizations, or how does
It
that
would be
work? You only have,
impossible
like,
to
one.
create. My whole point is that we know the source, okay? If the source has to be that big, it has to be 2,000 atoms, right? The single electron can't go 2,000 atoms away and 2,000 atoms away to create the photon. So the point is if we understand this spatial thing, the fact that it's actually in the space, the photon has changed space, thousands of atoms away from each other, the space has been changed, then it's just unrealistic to think one electron did that. One electron moved way over here and made something happen, then it went way down here and made something happen, then went over here and made something happen. It can't be filling that gigantic space with some form of energy. So it has to be made out of more than one hydrogen atom. More than one contributor has to be making the photon.
Well, in my, see, I'm not sure that, certainly it's bigger than a point, whatever this polarization wave is. So, I mean, you've got something that's heading in the transverse direction. I mean, it's got to be made up, I don't know, at a minimum of two things, probably more, so you can get at least, some reasonable 360-degree kind of thing before you start getting into, like, jaggies and quantization. But I don't know that it's, thousands of...
Well, how long is a photon? See, I would say if you just drew 5 circles on an envelope, take an envelope, draw a circle in one corner and draw a circle all the way to the other corner. 4 circles, 5 circles, 10 circles, doesn't matter. That's a photon. A photon is just bits moving parallel to each other from different points in space where they were released by an antenna. The antenna was in atoms. A row of atoms, a crystal, produced the photon one piece at a time in sequence. And so one bullet was fired, he's here. The next bullet's fired, he's here. Now this bullet goes here, this bullet goes here, and a new bullet's fired. So they're all moving in sequence in parallel. So if I took a gun and I fired a bullet here at the bottom, and then I fired another bullet a little higher, and I fired another bullet a little higher, and I fired another bullet a little higher, that would be a photon. So a photon not only has length, you have to have at least, like a frog could see 4 bullets. We need 6 or 7 or 8, whatever the number is. Okay, so a photon has length, and it has width, height. Okay, and it doesn't have any width, really small width-wise. It's paper thin. Okay, but that's what I would argue is a photon. It's energy coming at a frequency, and the energy is out of alignment. It's not at the same place in space, and that's the polarization.
Well, I would, let's see, now I have to admit that I don't know 100% about what the heck is going on with, light generation. So the way that I kind of see it is that, you have the nucleus and you have the little electron, and what we do know is that the energy that's coming out is quantized. So it doesn't come out at any energy, but it's just a matter of the electron is falling down and eventually hitting the nucleus.
All right.
And so kind of my thinking of what's going on here is that when it hits, it causes the atom, the nucleus, to resonate, basically. And the resonation, that resonating is then creating the wave. Now, like I said, like I would agree with you that it can't be, the wave can't be like only like one nucleus wide. It's got to be at least 3, at least 5, something like that. But it then sends out this wave, and my most recent discovery in my mind was that I'm thinking that the wave that's generated, basically has the shape of a rod. So it's just like a wave, and but that's just, it represents like a compression wave. It has,
I understand. I understand.
Exactly sure what it is.
Right. But you're not accounting for length. So I would say you have to make that rod, and then you have to extend another rod behind it and another rod behind it to account for frequency. The photon has a frequency. You can't just say rod, there, a frequency, I've done it. All right? I'm just saying there's lots of evidence that again, there are photons frogs can see. Why can a frog see a photon we can't? All right? And the reason is because they have a length. We need a certain number of rods to be right behind each other. So if you just took your rod example and turned it into my envelope example, then we agree. Okay, it's not a single
To a
rod.
certain degree, yeah, I would agree that they have to be repeating so that you have
You have to have
some
more than one wave to
continuous
have any.
frequency.
You can't even recognize a wave's frequency unless you have two of them, right? So you have to have at least two
Yeah.
waves.
So one of the questions is that if this thing is resonating, like how many times does it resonate before it stops? Is it like 3? I mean, it's got to be say a minimum of 2.
Well, let me just say, I used to believe in a resonant argument that electrons had a resonant frequency, but you really don't need it. So I got rid of it because you don't need it. It's completely unnecessary. Here's the simple argument I make to you. Okay, now just of a physical mechanism controlling all of this stuff. So let's just accept for a moment my theory, or even let's accept yours. There's an ether, okay, and I can compress it, okay, or however you want to describe the event. I can cause a change in it. So let's say I move towards the camera at the speed of light. What's going to happen? I'm going to collect every photon on towards me, and I'm going to reflect it. That means I'm going to get really bright, incredibly bright, right? Because I'm going to take every single photon that was in space heading for me, and I'm going to interact with it sooner than I would have, and I'm going to just give a burst of light. And if I move away from you at the speed of light, what's going to happen? I'm going to frickin' disappear. Not a single thing's going to reflect off of me. You're not even going to know I exist. I completely have vanished from the universe. Now, the funny part is, right, as I'm doing this, moving towards the camera, moving away from the camera, creating a frequency, while I'm doing this, what's the asshole behind me seeing? Oh, he's seeing exactly the opposite, right? When I'm getting bright to this guy, I'm getting dark to that guy, right? When I'm getting dark to this guy, I'm getting bright to that guy, right? So that is where you get entangled photons. That's the entanglement. One of them is out of phase with the other. A photon, when it's created by the very nature of its creation, is the movement of an electron. So the electron moves very fast, reflects a bunch of ether. I would call it force, but whatever. It reflects a bunch of force. Then it moves back fast. Doesn't reflect any, so that's the empty spot. So you have the frequency is a lot of light. I mean, a lot of force, a lot of ether. Then you have no ether. Then you have a lot of ether. Then you have no ether. Then you have a lot of ether. That's the pattern. That's the frequency. And that side of the universe is seeing exactly the opposite. So I sent a photon that way, and I sent a photon that way. Pieces of a photon, I would argue. But anyway, and the information I sent one way is exactly the opposite, the inverse of the information sent the other way. Now, to me, that explains as a basic physical mechanism how every time an electron moves, it changes the field. It changes the force.
I mean, that's interesting. I mean, that just kind of reminded me a little bit about when a positron and electron collide, that produces 2 back-to-back gamma rays. Why are they back-to-back? And, like you said, one of them might be sending forward, the other one has to necessarily be sent backwards.
Well, when an ultraviolet ray is converted into 2 infrared rays, the irony is they're not really back-to-back. They end up coming out, at 45-degree angles. So they're always somewhere on the plane of that 45-degree angle, but opposite.
I mean, I agree with pretty much everything you kind of said there. I mean,
right, it's a simple explanation of mechanics, right? So if we could agree,
I mean, I think kind of the envisioning of the light wave being kind of like, I like this card where, it's just coming at you, and if it comes this way, that's the polarization. If it comes at you that way, that's the polarization. That there's just something that has that transverse component to it.
Well, I think I could make you even better understand that, because I think you do understand antenna polarization. So I would argue to you that atoms in metals are, the geometry of metals is really interesting. You know what I'm saying? It's the crystals, right? So it's all crystals. So there's really hard geometry. So I would argue that that's the antenna for photons. The geometry between the crystals that create lots of facets, and the electricity runs across those facets, and that's actually the antenna for the photon. The photon is created on that junction, and it's created periodically. It's it's fires, 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 and it fires along that geometry, and that's the polarization of that particular photon. And the next photon is fired from this one, and the next one's fired from this direction, and this one is this, and that's why it's all mixed polarization, because each crystal is a different line, and each line is coming in a different direction, and so that's why the photons are all mixed in their polarization.
Although that's not the way it works with, say, radio antennas. So the way it works
Sure
with radio
it does.
is I have this is a radio antenna. Then we find that the best way to receive that radio antenna is to have one that's exactly the same in the same direction. So
Exactly.
if I turn the radio receiver this way, we find out that it doesn't receive very well. I mean, it doesn't
Exactly,
receive
but
nothing.
I'm just saying that that's exactly how the still you have to
But
that's
that's
what
microscopic
decides
thing.
whether a photon reflects or it doesn't reflect is how it hits the crystal. I mean, what's deciding? There has to be something that's deciding. Well, that's what's deciding. Is the polarization's inconsistent with the orientation of the crystal it hits, then it reflects. If it's consistent with the orientation of the crystal, then it creates electricity. So, I mean,
That's the antenna as a straight rod is crystallized in all sorts of directions.
I know, but you're not getting the point. The point is that it's the speed of the force. How fast the electricity goes up the antenna decides how long the antenna needs to be. So the antenna polarization, the fact is you need a longer antenna, the longer your wavelength, okay? So that's really just telling you how long does it take electricity to travel the path, and can I still have a frequency where it's not like halfway up the path? If my frequency is faster than how fast I can get up the antenna, I obviously can't use the rest of that antenna because I'm already supposed to send my second beep. You know, I've already gone beep, and now I can't send my second beep if I've only got this far up the antenna the first time. So I can't send a
that's
beep
true.
now.
I agree with that, but I would disagree with the transmission
I'm just
mechanism.
saying that it's all that we would call it all the same thing, and I'm saying, well, of course, antennas create radio waves. Why don't we think that photons aren't being created by antennas? The antenna is inside the atoms, and it's just that it's
Well,
2,000. It's
that's a-
2,000 atoms
Uh,
long. That's what electricity is. Electricity is going from point A to point B in a straight line, creating an antenna. The antenna creates the photon.
Because I don't think that that an atom is like an antenna.
I didn't
So-
say an atom is. I just said 2,000 atoms are.
Yeah, well, like 2,000 atoms are necessary. I mean, in your hypothesis, 2,000 atoms are necessary, and they all kind of need to work in concert, like they do in the metal antenna. Because what I see in the metal antenna is that you have the electricity. It's being the electrons are being pumped into the metal rod, and the voltage is rising on the rod. And in my hypothesis, what is happening is that the exterior electrons are literally getting pushed out of the surface of the metals. I'm betting that if you had a really, really good fast microscope and you watched a radio transmitter go, you would see the electrons, literally forced out of the metal and then coming back in. And what radio waves are is fundamentally, you take any electron and you wave it around, that will generate
I know,
waves.
but why doesn't exactly the same analogy work for a smaller path? Yeah, that's
Well,
exactly what
yeah.
electricity is. Electricity is malforming atoms. The atoms are changed in their appearance. That's why they're polarized. That's why they become magnetic. It's because you've now changed them from neutral atoms. You've compressed them. That means they got longer this way, shorter this way, and they became dipoles. That's why they become magnetic. It's because you've changed their shape. So I'm just saying to you, yes, when you're sending a photon onto some atoms, what you end up doing is hitting the atoms at the right location, and when it's in the right location, it pushes the electron just like electricity, and it changes the atoms that the electrons move into. So every time the electron pushes on an atom, it can change its shape, it changes its dipole nature, and now it's also a magnet.
I'm not quite sure about the whole magnet thing, but I mean the basic idea I think is sound, that something is pushing the electrons in, say, the metal rod, and then that increases the voltage pressure, and that's what we actually read out in our amplifiers and whatnot, right? I think that's a very simple mechanical picture that probably we can both agree to, but like mainstream is still stuck on this whole wave equation where the radio wave is this combination electric field, magnetic field thingy. I keep on arguing that that is just a bunch of hooey.
I know, but you're arguing that. So I would agree with you, right? That you don't. Well, first, the idea that it's two different fields to me is just, well, whatever. Who cares? It's a force, okay? I don't think there's two different fields doing anything. So there's not two kinds of waves traveling or any of that nonsense. There's not a magnetic field and an electric field. There's just a field of some sort of energy, some sort of compression in space that moves from one place to another. So I say it's a particle, you can say it's a compression. Whatever it is, I'm saying, yes, it's one compression. It's not both, or it's not, it doesn't change from electric to magnetic. It's always the same thing. It's charge. I mean, a magnet is charge, right? I mean, the north pole of the magnet reflects electrons. The south pole reflects protons. I mean, obviously a magnet is, magnetism is based on charge.
Well, no, it doesn't quite work that way. It's really, well, how magnets work is quite complicated. Really.
No, I don't think it is at all. I think it's quite simple, actually.
Right angle.
I know, but it doesn't change. Does the electricity does the same thing? So there's nothing. You know, the two are interwoven. It's all you're talking about is creating dipoles. Okay, and dipoles are charged. All right, well, let me just give you this analogy. Let me just real quick. Just say, for example, if I was to find a magnetic monopole, what would it look like? Well, in my opinion, it would look exactly like an electron and exactly like a proton. If I could stick the two of them next to each other, right next to each other, I would have exactly a magnet, right? So if I created another pair that was stuck onto each other and they were just charges, okay, no magnets, just charges. A plus charge stuck right next to a minus charge. And I made another plus-minus pair. It would behave exactly like a magnet. It would turn, it would flip, it would do exactly what a magnet does. So I'm just saying the two things are the same thing.
But the electric field and the magnetic field is what you're saying?
There's no electric field. Electricity happens in a conductor. There's no electricity anywhere else. There's only the magnetic field. That's the only, and it's not the magnetic field, it's really just charge. But regardless, that's the only field there is.
Repeat. I mean, do you think that the charge field is the same as a magnetic field?
Yeah, I just told you. I told you a proton and an electron stuck together is a magnet. I can't describe it as anything else other than that. If I stuck an electron to a proton, how could I say that wasn't a magnet? Because every experiment I do with it, it'll behave just like a magnet.
Well, the weird thing about a magnet is that if you took like a negative charge and you stuck it right next to the magnet, I don't care which pole, it wouldn't move.
It will. The problem is, see, magnets are filters and you can break them because they're always made out of metal. And the metal ends up being conductive, so it's a conductor. So you can change the charge on the outside of the magnet and thereby break the magnet. So yes, you can't bring charges next to magnets, but electrons always move away from a magnetic field.
No, they don't.
Yes, they do. Yes, they do. You can never put the north side of a magnet will always repel an electron. It will never go towards. It will never go towards.
Experimental evidence.
Okay, well, now, what? Show me. Okay, that's for a future video. Then for a future video, you can give me a reference to show me an electron moving towards the north side of a magnet. Show me one experiment where the electron moves towards the north side of a magnet.
Well, the experiment I'm pointing you out is that if you put an electron and it doesn't move, it feels no force from the magnet.
I'm saying there won't be any experiment where the electron doesn't move. You can't put it in the proximity of a north-facing magnet and have it not move. That's impossible.
Well, I'm saying that is exactly, if you did that
show me the experiment. Exactly show me that then. I'm saying show me the experiment. There's tons of experiments with cathode ray tubes and bending electron beams. Now, unfortunately, some of them have to do with what they put a gas inside the tube and they're really just moving ions around. But the electron will always either move up and down or away. It will never move towards the north side.
I'm not 100% sure about that, but I'm pretty sure that that there actually has to be some relative velocity of the electron in order for it to feel actually
Well,
any
I mean,
force.
it's almost impossible not to have an electron that has a relative velocity. So in the first place, it's almost
Yeah,
impossible
it's
to
very
create any
difficult. It's
kind of
kind of a theoretical
perfect
thing.
magnetic field where a charged particle says, I don't feel any tendency to move anywhere. Of course, it always feels a tendency. If I put it in this room, it would be impossible for me to place an electron in this room anywhere where it wouldn't say, it's positive over there. It's more positive over there. It would always find some place that's more positive and would head for it.
Well, I suppose how electric motors kind of works that way in that the electrons inside the wires, inside the motor, if they're not moving, no electromotive force
No,
is
no, no.
generated.
See, I would argue that the people
Putting
completely.
current through, do the electrons actually feel any force inside the
The
magnetic
current
field?
is
One demonstration.
the current is superfluous. What the electricity is doing is causing the wire to become magnetic. That's what's creating the motor force. So all you're doing is turning the metal into a magnet when you run electricity through it. So any conductor, any medium, even a bunch of ions, as soon as you put electricity through them, when you ionize them, you bipolarize them. You change them into dipoles, the atoms. So the atoms went from being neutral to being the wrong shape, which is the electrons are going this way and the proton is fat this way. And so from different perspectives, it can be viewed as being positive on both these sides and negative on both these sides. So the point is you polarize the atom. So as soon as you polarize an atom, it's a magnet. I mean, if the polarization is consistent, don't get me wrong. Obviously, if all the atoms are in different arrangements, then all the magnetism discounts itself. But I'm just saying when you're running a current, it's all in the same direction. So they all have the same geometry. They all line up and they create magnetism. And the magnetism is what's fighting the magnetism. You're just pushing magnets with magnets. You made the wire.
The nature of the magnetic field. Still, I mean, why
the field isn't just a magical field. So again, I can explain the magnetic field, but it's going to take more than just show to do it. You have to be willing to watch some of my videos. But I can
explain the magnetic field as a aspect of the electrostatic force.
Well, I know, but you think that's causing gravity too, and I can give you lots of counter examples of how that's not possible because where's the repulsion? You can't make a charge that's pretends it doesn't do the repulsion thing anymore when it does, and so it's never going.
What do you mean by the repulsion thing? I mean,
all I mean is that all I'd have to do is make a Venn diagram machine, and it should be flying up into the atmosphere. It should be taken off like a rocket. All I have to do is make a positive. I mean, put enough negative charge on something, and it should be shooting up into the atmosphere.
Well, technically positive charge, but I did do some experiments where
more electrons.
I had a graph generator, and I emitted positively charged bubbles, and
I know, but we know we know that wasn't exactly a perfect clinical experiment. So
it's not a clinical experiment. Although I was thinking that Elon Musk should be interested in this because all you do is charge your rocket up as high as you can positively charged, then you will probably substantially reduce your fuel.
If you're right, that charge has something to do with gravity and has nothing to do with it. I got gravity nailed, frankly. But again, you got to watch some. I can give you the quickie on it, but I mean, it's no point. The context is the context. You could probably watch a half-hour video and get it better than me trying to explain it in this show. But, I mean, gravity is just the absorption of the energy from this field I keep telling you exists, these soldiers. All there are is soldiers. The soldiers run the speed of light, and the soldiers crash into shit. And that's what the universe runs on. And so when a soldier crashes into something, he gets his knife stuck on it, and he keeps pushing it for a little while until another soldier hits, and then he bounces off. But the point is that the force gets used up a little bit by moving matter. So every time you move matter, you basically stole a little bit of energy from a force. Every time you move a piece of matter, the force that pushed it didn't get where it was going. So it went a little less distance in the same amount of time, which means it lost a little bit of momentum. And that little tiny bit of momentum is lost every time an electron jiggles around. It's using up a little bit of force, and that means that more energy goes into the Earth than comes out of the Earth. Because the Earth has a bunch of electrons and protons moving around, so they've used up a little bit of energy, A little bit of time has been wasted by the soldiers pushing electrons and pushing protons slower than the speed of light. And that tells you why there's gravity. It's because you have a net loss in momentum.
Well, that could be, or it could not be. It's
well, I'm just saying it does fit. It does explain.
You can't really determine the truth of these things, unless you can find your little soldiers, right? Experimentally.
Well, I don't need to find them experimentally because we have a ton of experiments. All I have to do is show a huge consistency by the little soldiers work for gravity, the little soldiers work for charge, the little soldiers work for magnetism. Then I've done my job.
I don't think that's enough.
Well, I think matching all the experiments and explaining them with a mechanism, I don't think there's any possibility of doing that unless you have the right answer. So I haven't seen anybody else do it. Where's somebody else's elemental theory been something simple, okay, a soldier banging into snowman? How does that ever be able to explain the 5 phenomenon? If we said there was 5 phenomenon: photons, magnetism, gravity, electricity, and whatever else you want to make up for the 5th one.
Yeah, well, I explain all of that just in terms of positrons and electrons. I think I can explain all of those things. So,
well, I read your papers. I'm just saying I don't think you can explain gravity with charge. I just think that's never going to work.
Well, well, why? I mean,
because charge is by its very nature positive and negative. If it was true, we'd see it. We'd measure it right now. Why can't I measure this charge difference that you say exists? You're saying 10 meters per second per second. There's a 10 meter per second charge difference. Where is it?
Well, if you actually have an electrostatic meter and you put it on the Earth, you will find that there is a 120 volt per meter electric charge. You're sitting in an electric field. Definitely that's experimentally measured, right? We're talking about experiments. This is experiment you can do. If you can get an electric meter, you can measure the electric field strength on the Earth's surface.
I know. I just gave you the example, though. Why don't I just create a charge, okay, that's repulsive to the Earth's ground? All I have to do is create a charge that's a higher negative charge than the Earth's ground, and the thing should shoot up like a rocket. Why doesn't it do that?
It probably would, except that we have neutrons make up half the mass of everything, and those neutrons are still attracted to the Earth. So you have to.
I can't even overcome the attractive force. Why the attractive force shouldn't even exist? So why do I have to even overcome the gravity? Because it shouldn't even exist. If I'm oppositely charged, I shouldn't even have to overcome gravity because I've already destroyed it by being positive. I mean, negatively charged.
Well, I'm saying that you have to understand that the part that is attracted due to the charge is actually the neutral dipoles. And it's like...
Well, what is a neutral dipole? In the context of us knowing that electrons, the number of electrons decide, okay, whether something is voltage-wise positive or negative, right? So that's electrostatics. That's all about the number of electrons. So there's no such thing as anything called neutral. There's only ground to the object. So the Earth has a specific ground state, but it isn't anything called neutral. It has a certain number of electrons. You can make less electrons, you can make more electrons, but there's no such thing as neutral.
Well, no, I mean, between a positron and electron, or between a proton and electron in your body, those form dipoles. See, now my hypothesis is that if you were to look at the dipoles in your body, you would find that they are all pointing towards the center of the Earth because they've taken alignment, and because there's one positive charge slightly closer than the negative charge, that's what actually causes neutral objects to be attracted to any point charge.
So you think that when two static objects are attracted to each other, it's because their atoms inside of them has changed, not just the surface atoms. It's not just about surface electrons. Now, I would argue that all the evidence indicates that charge is a surface phenomenon. That's all it is surfaces. Okay, and only when you're talking about conductive metals can you charge the entire material, but it's always a surface phenomenon.
Well, I think let's say that the case of the Earth, or actually astronomical bodies, is that electrons are relatively easily lost, Now, if you take your comb and you put it through your hair, or you can rub a balloon in your hair, that's lost electrons. And then you can take that balloon and you can stick it on the wall. I mean,
right, I know, but the point is you didn't go neutral. You're either something relative to some density number, okay? So the ground ends up being the big giant Earth that has all of these different influences, and it comes up with some number, and that's its electron pressure state. It has a voltage, 0. Okay, but 0 voltage doesn't mean neutral. Okay, it just means the Earth is at a ground state. It just means that it has a state. It doesn't mean neutral. And I'm just saying I still should be able to make a body that is less electrons, less pressure, and that would attract, right?
Yes, I mean, you should. And if you actually perform that experiment, I'm betting you would find it's true.
I'm just saying we already performed the experiment.
Charge for it to fly off the Earth, unfortunately, because like the charge that's under our feet is something like the equivalent of like a million volts. So it's very hard to generate opposite million volts because it would immediately short out with anything that's.
Well, again, it only shorts out because of the atmosphere. We know that charge doesn't even move in empty space. I mean, well, whatever. You can. I mean,
there are some people
you may pursue.
Or whatever, who said they actually kind of did that they charged these like umbrella type things and they made it.
I'm betting it won't work from the top of a mountain, and it won't work from the bottom of the sea and all of that stuff because gravity is nothing. It just doesn't have anything to do with charge. Sorry.
But I mean, you challenged me to say that like if the charge exists, then where is it? I'm telling you, if you look at
I know, but it doesn't make any sense still to me. There's absolutely, you have given me no reason why I can't make something, okay, that is the same charge potential as the Earth and create a very strong repulsion.
Yes, you could. Other than the fact that it would take like 2 or 3 million volts to do it.
Why would it do that? Why would it? Well, even if it took 2 or 3 million volts, we can get that on good Venn diagram machine. Can make 1 million volts. So we've already done the experiment, and the Venn diagram didn't fly up or do anything, or didn't show any signs of anti-gravity function.
Well, like I said, within the limitations of what I could do, which is like soap bubbles. It did seem to show.
I know, but you have to concede that isn't that a rather abstract experiment, right? So okay, so here we're taking soap bubbles, so you blew them through some sort of plastic hoop, okay, that we know doesn't charge very evenly. So you can't even be sure you charged the piece of what did you blow the bubbles through? Because it wasn't a metal conductor. You can't even be sure the thing you blew the bubbles through that had the soap on them was actually at the high voltage potential, right? Because a piece of plastic.
So you can do it with the Van de Graaff generator off. You can do it with the Van de Graaff generator on. You can do it actually.
I'm just saying to charge a soap bubble. I'm saying there's a whole bunch of physics just to whether that's even possible. First, that you could even charge any water or anything else, that you could charge it merely by holding onto a Van de Graaff machine and saying I'm going to charge a bucket of water. That even is questionable because of water's lack of conductivity. All right. The fact is, it's not that easy to charge a bucket of water.
At those voltages, I mean, it's quite clear that the entire human body becomes charged. Because,
so
like your
what?
Head,
I said your surface becomes charged. So we're back to the argument. Your whole body doesn't become charged, just the surface.
Well, something becomes charged. Clearly, the electricity is clearly able to flow at least to
No,
your head.
it doesn't flow. No. It's just electrons sticking to your body. That's all it is. You either get covered with electrons or we take electrons away. But that's all that happens. Nothing happens to the inside of your body. It just happens to the outside. We either take electrons away or we put electrons on top of you. We either color you with dust or we blow the dust off. But that's all there is.
So technically, I was using a positive dome Van de Graaff generator. So technically, I was sucking electrons out of whatever I was holding. So to leave it a net positive charge.
Right, I know, but it doesn't. I'm just saying it doesn't really matter. The point is that charge is a phenomenon on the surface. It's the free electrons. It's not the atomic electrons that have anything to do with charge. Charge just has to do with sticking extra electrons to something. So you either put them on the surface. They say, "Hey, there's a whorehouse. I'm going to try to get in," but they're not part of the atoms. They're just lookers trying to get in. And that's all it is, because the proton creates a little bit of extra positive charge, for them to linger in. And that's all they're doing. And you're either saying, I'm going to peel those off, or I'm going to throw more on. And, but...
Well, in any case, we're talking about gravity. So one of my main hypotheses is that all of these forces, gravity, magnetism, and charge, are actually all just an aspect of just the one force, charge, which is kind of something that science tries to do, which is try to unify things, right? So that would be one advantage versus, your force carriers, which would actually have to be something distinctly different than, I don't know, charge. I'm not exactly sure how...
I know, but you're not going to give me anything that's going to tell me how charge does push and pull, because I'm going to argue there is no pull, okay? So all you can do is have...
I totally agree that there's no pull.
Okay, so
positron and electron, the only reason why they're coming together is because there are a bunch of other things pushing them together. This is what...
Well, I mean, as long as we can understand that, then you have to come up with two forces. So this is what, because I went through this path, frankly.
Yeah, I mean, the
forces... You have to have a positive force and a negative force to go with the positive electron and the negative proton. The negative proton.
There is no positive and negative. All there is you have the forces being generated by things colliding into each other.
Well, again, then that just. I'm sorry, I won't be able to go for that because charge is obvious to me. I don't know how De Hilster does this too. He just negates the existence of charge and pretends you can do it with one thing. You can't do it with one thing. It's clearly the same conditions. I create one condition. I create one condition. Let me just make the argument. I make one condition. Okay, it's a condition. I've created a condition in space. The fact is, if I put an electron in that condition, it goes that way. I put a proton in that condition, it comes this way. How do I have the same exact condition create two different effects?
I can explain that.
How?
My hypothesis is that the electron and the positron, what they are doing is that they are generating waves like a resonant frequency, like a bell. So pretend the electron's like a bell. We have a positron.
All right. Well, then you do have attraction because they're not pushing waves then.
No, they're not. If they were not pushing waves, they would not do anything. But this is what I'm thinking. The only difference between the positron and electron is that they're ringing, right? They're going like they're doing something that's pushing out waves, right? Now, they could be doing, random stuff. But what I'm thinking is that the only difference between the positron and electron is that they are at opposite phases. So they're going like this. Right? They're going at opposite phase. That's the only difference between the positron.
I know, but every time I change the distance, then I'm going to change whether they're in phase or out of phase. So I just move one of your hands.
The thing is that if I have two electrons, they're going like this. So they're both pushing out waves at the same time. And in between the waves, we would know that as adding, right? The waves are adding.
No, all I do is change the distance. Again, if I change the distance, I change the phase.
Well, the thing is that another hypothesis is that space at this level is actually quantized. So an electron cannot be any arbitrary distance away from another electron. That has to be either here or here or here or here or here. And that corresponds to the phase that's possible between the two particles. So that is a hypothesis. That's a postulate, I guess. But that makes it impossible for anything that these guys are doing to actually be out of phase. It has to be either 100% in phase or it has to be 100% out of phase. It's binary.
And why would out of phase be attractive? Why would they move towards each other?
Well, because this creates a destructive interference that between the electron and the positron, the waves are canceling each other. So
what?
Any pushes and pulls are basically canceled. Now, this makes it the opportunity, because we still got particles on the outside constantly pushing against the outside. But then you've got fewer particles on the inside because these waves are canceling, that the forces that are coming out are being canceled. So there's less force. I know,
but all the waves on the outside are also being created by positrons and electrons that are forced to be a specific distance from this electron. Okay, so if I have one electron here, you're saying this external field is creating waves that aren't destructive, right? But the only ways it can do that is the only way that can happen is the electrons are the only ones it can be interacting with. right? And you're saying that all the positrons out here are also creating attraction.
Well, you do have. I mean, that's an interesting argument because I mean, it does have to do with the quantization of what the heck else is going on out here, right?
Yeah, well, I have a natural, just a revulsion to the whole wave stuff and this whole interference thing being critical to anything. And the whole idea of canceling energy really irritates me. I'm just saying that you'd have to account for the energy that's destroyed. Well, what do you mean it's destroyed? I mean, can you really do that?
Actually, you actually don't have to care about the actual incoming because as this thing is pulsing, that alone is creating the pushing force that you need to push the two things together. It's just that between the two particles, that force is somewhat canceled out.
Well, I'm just saying it's annihilated. So I'm just saying you have taken energy out of the universe by putting two things in proximity to each other. So I'm just saying that has to be accounted for in the sense that the density of the pressure isn't because you changed where the pressure went, you've destroyed it. And that's a fundamental difference.
It's just like noise canceling headphones. I mean, when you do that, did you?
I know, but they're media. That's in a medium, and again, so I don't want to make medium-based arguments all the time. But I mean, that isn't true of light. So the point is that the photons don't get destroyed; they just get broken, and you can recombine them and remake a photon. And that's why. I just
want to get back to the whole argument about you asked how does the positron attract the negative? How can you create any kind of attractive forces without having an attraction, basically, right? So,
right. I'm just saying that you're saying they're pushed because you annihilate the force between them. Okay, so that's what you're saying.
Yeah,
they're saying there's an absence of pressure between them because the two forces are incompatible. Therefore, the forces aren't going to be felt as forces, and so the external world pushes them together. So in that sense, we have a consistent theory. Okay, because that's sort of what I'm always. It's always push. It's always push. So there's always wherever something looks like it's attracting, it's not really attracting. It's that you've taken away the repulsion. Okay, you've taken away the pusher. So it's like having a tug of war, and you just one side stops pulling on the rope. Well, yeah, the rope's going to go the other way because no one's pulling the other way. So it's that simple. No one's pushing on the rope the other way. But yeah.
Yeah, but getting back to how this works, I mean, it's also been experimentally confirmed. I mean, this experiment was done about 100 years ago, and the guy was using water, and he was using like drums, which had diaphragms on the outside, so he could pulse these things. And he found that when he did that, he would be able to get these attractive and repulsive 1/r² effects. So when I saw that, I mean, that's kind of what convinced me to think that this is the actual mechanism for attraction of opposite charges, because you can actually do physical experiment that actually creates exactly that kind of force using these kind of phased arrangements. But like you noted, it's the phases has to be fixed, right? So that otherwise, if the electron is like half a wavelength away or a quarter, then the attraction and repulsion wouldn't exactly cancel out, and it just wouldn't work. So
I don't know, how did this guy quantize the experiment, because that's the trickiest part of it. I mean,
the thing is that if you're using ordinary water, you just have to make sure that the wavelength is of a specific length, so that when they come together, they just naturally don't. I mean, you have to actually set up the experiment so that you are in phase, right? Obviously, if you set the experiment up so that you're not in phase, you use the wrong frequency, then it's not going to work. But if you
well, I know, but you couldn't have them have any continuous motion without forcing the motion to be in your quantum steps of wavelength. So they have to be within wavelength steps of motion. I'm just saying, when you saw this experiment, how could he make the object obey your rule that it can only exist at these 2 points or these 2 points or these 2 points? How did he force that?
He just physically set up the experiment, so he used the two bladders, so they're not like one wavelength apart or two wavelengths apart. That he just but the main thing was to show that if you did it in opposite phases, that they would attract, and if you did it in phase, then they would repel.
Well, so you saw a little bit of movement in one direction or another direction. You didn't go outside of that real tiny bit of movement, right? So it was just a small amount of movement. He didn't move anything, any distance.
No, it's probably just he just probably put a little force meter on it, and
okay.
Yeah.
Well, I'm well, okay. So I'll think some more on why that can't possibly be the truth, but I'll get to that. But yeah, my theory does it in, like right? Name that tune. I mean, my theory does it in 2 notes, okay? My theory does it even quicker, so it doesn't even need any of that crap because it just creates 2 forces and makes it easy.
You're postulating that. I mean, in my system, that behavior is
you just postulated a whole bunch of stuff. You just told me I need all these. I got to have space that's geometrically spaced, okay? And it has to be the wavelength of all the electrons have to have the same wavelength that they're all pulsing at, and they all have to be like jellyfish, and they're all the time doing this jellyfishing thing for whatever reason. So, I mean, yours is postulating a whole bunch of mechanics. I'm just saying mine's really simple, okay? There's red balls and blue balls. You hit me with a red ball, okay, and I move. You hit me with a blue ball, and it bounces off that way, or that way, or that way, or that way. And I don't move. And there, I can solve magnetism and charge. So, I mean, all I have to do is create 2 forces, 2 kinds of charge, electrons and protons, and I'm done. So I create red and blue.
Yeah, well, you're saying charge is charge. I mean, but
I didn't say charge is charge. I just explained how there's 2 different interactions. Okay, just like you're in phase and out of phase, exactly the same thing as what I just proposed. 2 kinds of interactions. Okay, red ball hits me, I move. Blue ball hits me, the ball bounces off of me. 2 different interactions. Explains why there's a lack of pressure and why there is pressure. So that's all. I'm just saying it's just as simple.
I mean, it's still a pressure argument.
It's exactly a pressure argument. Obviously, if somebody throws a bunch of blue balls at me, I don't move. If somebody throws a bunch of red balls at me, I move like fuck. I move really fast. Okay, so yeah, that's a big difference. In pressure.
But why does the blue and the red balls do different things?
Why does the in-phase wave, why is the positron creating a wave that's out of phase with the electron? Well, it's you have the same question you're not going to be able to answer. Why don't we just ask, who's God?
I can emulate that, like that other guy with the experiment. It's like, well, if you set up that system...
I'm just saying that I can do it in fewer notes. I can do it in fewer notes. I'm just saying that it's simpler just to have red and blue balls matching the red and blue electron and proton. So if I just make the force just like the matter, I make 2 kinds of it, I'm done. That's all the pieces I need. And then 2 interactions. So I have 2 kinds of force, 2 kinds of matter, 2 kinds of interaction, and I'm done. And I can explain all movement in the universe.
Well, it might be true, but I still like my theory a little bit better.
Yeah, that's okay. I'm just saying.
I don't have to define things that way. I mean, I just have to use Newtonian mechanics, but I
see. What Newtonian, he didn't. There's no such thing as Newtonian mechanics, so I hate that word too. Newton didn't even describe mechanics. He said, I don't know what the mechanics are. He said overtly, I postulate no mechanics. And now they say Newton's mechanics. It's not Newton's mechanics. He didn't have any mechanics. He barely even knew the speed of light, right? I mean, it wasn't until he was pretty old that he even knew that light might have a speed. So, I mean, come on. There's no Newton mechanics.
Well, maybe the mechanics of billiard balls. How about that? Like I said, I keep on going back to say billiard
balls. Yes, exactly. And all I'm saying is the billiard balls don't move because cues hit them. They move because littler billiard balls hit them. And when a blue ball hits you, one thing happens. When a red ball hits you, something else happens. And if you're red, the opposite happens.
Comparison is like, I would disagree. I would say if the billiard ball moves, it moves because it got hit by another billiard ball. It didn't get hit by bees or the atmosphere. It got hit by another billiard ball.
Well, I know, but then you don't have force anywhere. You don't have any mechanism moving the speed of light.
Well, the mechanism I have moving at the speed of light is that, at the, say, ether particle level, that any interaction at that level is happening at the speed of light. So and the speed of light.
I know, but you're still saying it's like the amount of
along.
energy being transferred is so much tinier than the actual object. So I mean, it's just like, the amount of a tiny bit of movement by an electron is a huge amount of energy in terms of, photonic potential or whatever you want to call it. So I mean, it just doesn't seem very realistic to make the universe out of these big giant things that are moving just a tiny, tiny little bit to create a tiny, tiny little photon. When, the real game is that there is small spaces and everything does hit small spaces and the force is really small. The elemental force is really small. And, again...
it just seems like, your elemental force is almost equivalent of, say, my ether particle. I mean, they're both small, they're both everywhere, they both carry energy. I mean...
I know, but your ether particle, I just pointed out, your ether particle is big giant things. It's not a little ether particle. You have big giant positrons and electrons. Those are big things by comparison to a force.
Yeah, although, like I said, I would argue that that's kind of an incorrect use of the word force. I mean, I think you should name that thing something else. I don't know. But that's neither here or there. But I think that, when the positron and electron get together and form, it's effectively a neutron. It's like a neutron seed. And those things, what exactly do we mean by size, anyways? Because these things interact largely through their sphere of influence of their charges, right? So, but I'm thinking that it's a fairly dense sea of positrons and electrons, but they are of the order of the size of, say, another electron. That's why I was saying.
All right. Well, let's say
arguing is saying that
let's say I could prove
through a field of things that are about the size of the electron. So
let's say I could prove that there was 2 trillion vectors that something could move at, or a trillion times a trillion. So it's like you could go any straight line from a single point. And I could cut it into 1 trillion paths. How could a field of protons and electrons create those paths that would be straight lines? Say if I wanted to send a photon from a star that's 10 billion light years away. I'm arguing a single little bullets are coming from that sun. Okay, so they're traveling dead straight lines and just flying from that sun. You're saying they're traveling a pathway of electrons and positrons. Well, how can they do that? Because there's no geometry for it. There's no straight line of electrons and positrons that'll get me from here to that star.
Well, maybe not. Maybe there isn't. But it could be just like your screen that you're staring at is that, that thing is made up of millions of little light emitting things. And if they're close enough together, we can have something that looks like a straight line. But if we looked at it really closely, we would see that, no, it's not exactly a straight line. It kind of goes this way, then goes this way.
Right. So then we'd have to say that there would be, then we would say that the speed of light then had to be variable.
Light would just have to be, like I think we both agree that a photon is, something bigger. I don't know how big it is, but it's certainly not a point. And it takes some... whatever the units are of space for it to travel through. So, but that is something that I can neither confirm or deny or point out to any experiments to say that a photon coming from Alpha Centauri is not going to take any detours on its way to Earth. Even though it's going through a particulate quantized medium, it just seems to do that. That just seems to be one of the base properties of a photon that, like I said, it travels like, totally straight. And that doesn't sound totally consistent with it going through some particulate medium. But, we see, we know that water is, similar particulate medium, and we can shine a laser beam through that, and it doesn't seem to deflect.
Well, it
Well,
does
it's like
though. It
some,
does.
but
It does because the light takes twice as long to get through. It's a 40% degrade in the speed of the transmission of the light. So obviously, it's not traveling a straight line.
it's vector wise, it's traveling.
Well, I'm just saying that it can't be physically if it's still moving the speed of light. So my argument would be if the energy is still moving at the speed of light, there has to be something happening to its path. Or you have to be physically slowing it down because it's pushing electrons and protons, for example, and that slows it down. That would be my example.
One of the things I kind of hypothesize is that the medium, whatever it is basically frictionless and completely lossless. And if it actually got
again, I just don't know why. See, it's so unintuitive for me to choose a medium, and it's so intuitive for you to do it. It's just a weird. It's a real.
Because I see mediums. I see water. I see air.
I know, and they're nothing like empty space to me. There's not a single thing they have in common. I mean, mediums are exactly that: clunky, dirty, messy, sloppy. Empty space is clean, pure.
Going back to experiments, we can measure properties of empty space like permittivity and permeability.
No, those were never measured. Those were never measured. There's no such thing. That was a made-up constant. Both of those are they call look it up. Look it up now. Look it up now. They call them the electric constant and the magnetic constant. They changed their names because there was no such thing. There's no such thing as the permittivity of space.
Well, there's a permittivity of the plastic that my lens is made out of. I mean, these are properties.
Those are mediums. Yes, I'm just saying there was no measured constant. I'm just saying there was never any measured constant. And the whole thing is it was the only thing that was ever measured was the speed of the force, and that is the measured constant. Is the speed of light, the speed of the force.
No,
that's why the two constants added up to the speed of light. If you take the two constants and divide them into each other, they turned out to be the speed of light. It's because they were always derivatives of the speed of light. They were always derivatives of one force. They were never measured constants.
But my point is that those properties are the properties of air and water, any transparent substance. You can measure those particular parameters, and when you measure space,
because they're full of atoms. I'm just saying that I just don't. Again, well, whatever. There's no point. I mean, I just don't know how that is intuitive to you because it's completely alien to me. I mean, I can't even tell you how unintuitive the idea that space is made out of Jell-O is. It just doesn't mean anything to me. I'm like, fuck. Why would it be made out of Jell-O? Okay, there's something, and there's nothing. I mean, there's such a thing as a nothing. There's nothing. Yeah, there's nothing there. Okay, I could take a little bottle of space and there'd be nothing in the bottle of space. Nothing. There wouldn't be something in there. I mean, it's like the Einstein thing.
It goes to our differences in, say, how a photon travels. I mean, for you, a photon is literally a particle. It goes from point A to point B. Now, for me, I think that the experimental evidence is that light is a wave phenomenon.
No, there's no that evidence sucks though. So you gotta watch my two slit experiment videos because it's complete nonsense. The two slit experiment is complete nonsense.
And the other thing is that I believe that it seems to be characteristic that things which can travel long distances are typically wave phenomena. So like if I put a red dye on one end of a swimming pool, it would take a long time for it to get all the way to the other side. Versus if I put a speaker in the swimming pool and turned it on, that sound wave would get to the other side in like a millisecond.
Well, obviously one is energetic though. So if I made your dye, if I gave your dye energy, that is I made the little dye particles, I gave them the same amount of voltage that you put into the speaker and gave it just as much dynamic energy, it would get across the pool just as fast too.
No, I don't think
those atoms would be very energetic. Yeah, they'd be like radioactive. That'd be like alpha, radiation. It'd be zooming out of that thing, and transferring its energy. I mean, it has the same energy transferring problem. I mean, obviously, sound waves. We're talking about things that have a speed limit, and so I've already made this argument to other people. But well, let me just see what you would say to this. I would argue that all sound is created by moving something faster than the speed of sound. So you're actually creating little sonic booms. So our Larynx vibrate faster than the speed of sound. They create little tiny sonic booms. The sonic booms go into our mouth, and we change the frequencies and blah, 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 and all that kind of crap. But all sound starts with a little boom, a little sonic boom. So every time anything, any material object moves faster than the speed of sound in the atmosphere, so it has to be in the atmosphere, obviously it has to be a piece of matter sticking into the atmosphere and moving the atoms in the atmosphere, that movement is what actually creates. So all sound is really little sonic booms. And that sound just means that you're banging two electrons together so efficiently, so fast, that, that two atoms, that when they hit each other, they always transfer the energy in a straight line. Where that if you hit them slow, the energy can go up and go down. It can go all kinds of directions. But if you hit them fast enough, it's like a bullet going through somebody's brain. If you're moving the bullet fast enough, it takes really no brain with it. But if you do it slow, push the bullet through with your finger, it's really messy. A lot of tissue gets torn, a lot of shit happens. So it's, sound is just the idea that you violated the speed limit with which the electrons can react to each other. So you're forcing them to get too close to each other way too fast. They build up too much pressure, move even quicker away from each other. And so the sound just creates a quicker medium to transfer the energy. And quicker, I just mean more efficient. There's less waste, less misdirection. So you just force it to go in straighter lines. So sound is really, or water waves are really just vertical straight line force again. It's really just atoms pushing on atoms and in straight lines. And that's why it goes great distances, is because all the energy keeps going in one direction. It doesn't go a little bit this way and then a little that way and a little over here and a little over there. So you didn't use it up creating noise. You kept the pool balls moving really quick in a direction. So if I line up a bunch of pool balls and I hit one of them, it bounces really efficiently through all the balls. But if I hit it slowly, then the ball can go a little this way, it can go a little that way, a little this way. I can not even hit the fifth ball.
Well, I mean, that's all true, although I'm not quite so sure about the whole speed of sound thing, because I've got my nice speaker system and I can see the woofers going in and out and generating sound, and I don't think they're any at all.
But that's all you see. But that's all you see.
Sound.
You're seeing the movement. You're not necessarily seeing the movement, right? So you kind of know that it's a much smaller thing that's actually doing all this wiggling. So I'm just saying that I'm just arguing that the real movement, the real acceleration, is faster than the speed of sound.
Yeah, I'm not so sure about that. I mean, although I'm not sure that really makes any difference to the argument, whether it's the speed of sound or not. I mean, typically, anything that exceeds the speed of sound, like a bullwhip, does leave a specific crack in the air. That's.
I'm just saying that's the cliche. That's the perfect example to me. Is that really illustrates it though? Why does that happen? Why is a little thing creating a sonic boom? And you could just imagine, well, I can just take every example of sound and I can say when you dissect them, you can find something moving faster than the speed of sound. You can find little parts, little hairs, little bits that are moving quicker than you think the whole object is moving, and that's creating the sound.
Although I'm not quite sure where this whole thing was going to. I mean, we're talking about...
Well, it goes to carrier frequencies. Remember, you made the argument against my argument about light. Okay, I propose that the electricity going in can't be a square wave. It can't be a sine wave. It's either on and off. It's a completely digital signal that is always the carrier wave for a radio. You can never send, okay, as the carrier frequency, a shaped wave. You're just sending on and off.
Now, that is true that I tried to look that up, and I couldn't actually find someone actually doing the carrier wave experiment. Although I do know that in AM modulation, that's amplitude modulation, they're using the actual amplitude of the wave to encode information. So certainly they can do that. I mean,
Well, I'm
it's
just saying,
not-
as soon as you say modulation, you're modulating with another frequency. So that's my whole
yeah,
point is
you're
that
isolating it
the
with the
carrier,
amplitude, so you have-
I know, but the carrier can't be changed in its shape. All you're doing is putting another frequency on the carrier. You're not changing the shape of the carrier. You're putting a shape on the carrier.
Modulation, I mean, the additional information is being carried on the amplitude of the carrier.
It
So
doesn't. It doesn't.
You get a
It,
big wave, and then you get. I mean, there's all sine
it
waves. but
still doesn't change. The carrier wave is the higher frequency wave.
No, I mean when AM transmits at like 770 hertz, there's a constant 70,
Right, and the
70
AM signal is the high frequency. You can't change the shape of the high frequency wave. You can only create a shape of that. You can take that slinky and move it around, okay? But you can't change that slinky's frequency. The frequency of the carrier can't be changed.
You can change the amplitude.
But you can't change the shape.
Radio waves.
All right, there's no point in you
look
saying
at
it
how
over and
radio
over
waves-
again. You can't
it's
change
so
the shape of the actual pulses that go up and down. You can't change the shape of. So here I got a pulse, I got a pulse, I got a pulse.
Well-
I can have half a pulse, half a pulse, half a pulse, half a pulse, 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 pulse. Okay, I can put a square wave, I can make a square wave out of the pulses, but I can't change the on and offness of the pulses. I can't change that wave into a square wave.
Well, you can change the on and offness, and that it can be twice as on or 3 times as
Again,
on,
that didn't
or
change
1
the
times as on.
didn't change the shape of the wave. It just changed how high or low it went. It did not change its shape.
You can change how high. or low it
Sorry,
goes.
it didn't change the shape of the actual. Again, you're just not listening. Draw it. Draw
I mean,
it.
It's still a sine wave. I mean, we didn't change.
No,
that.
it's not a sine wave even. There's no sine wave. It's on and off. It's completely binary. There is no frickin' wave.
AM radio wave is definitely not binary.
It's definitely
It's not
binary.
height.
It's on and off.
If you change the height of the wave, as you admit, as
It's
can
how
happen-
many photons you're sending. You change the height by sending more photons. The amplitude of the wave is controlled by what volume of photons you send. Not at what frequency. It's the volume. Amplitude is volume.
volume. So in the larger amplitude wave, you're sending like 16 photons.
Right, and then there would be 8 for half of that much, and then 4.
Some variable amount of photons.
Right, you're just sending more energy. You're sending more bits.
Well, I mean, I would disagree because it's like if you put it, if you look at it with electronics, the shape gets taller.
Again,
So
there's no shape. That's on an oscilloscope. That's on a trace. A trace is forcing the shape, just like your heartbeat isn't, a sine wave. Your heartbeat is freaking ions go shooting across your heart in a millisecond. Okay, there's no sine wave. There's just boom, pow, shoot all the muscles, fire. There's fire, don't fire. Fire, don't fire. There's no sine wave.
Well, I'm still scheming on actually seeing if I can do this experiment. I've got my 101 electronics kit, and it's like I can build rudimentary transmitters and receivers with it. So theoretically, I should be able to build a square wave carrier transmitter, and I should be able to receive it. And I should
Think about what you're saying for a minute, though. Just think about what you're saying for a minute. Just think about what you're saying for a minute, all right? So I'm saying to you that's theoretically impossible because I'm saying a photon is a timed event. You can't make a timed event that goes, I went on and I stayed on for a while, and now I'm off, and now I'm off for a while, and then I turned on and I stayed on for a while. How does a photon do that staying on for a while? It can't really do that. It has to send either there's a quanta or no quanta. You can't make it do anything else. It either is energy or no energy. It's either saying push or not push. But it can't.
I mean, that's the difference. I'm saying it's not doing that.
I know, but there's absolutely no evidence that it isn't. That's what the whole electric, the photoelectric effect kind of demonstrates. That's what this whole Planck quanta thing decides, is that you can't change the length of that. You can't say it stays on this long or some other period because that changes the frequency. So you're stuck with one shape of wave, which is basically just saying, on and an off. There's nothing and then there's something, and then there's nothing and then there's something, and then there's nothing and then there's something. It's always binary.
Or, I look at it like, generating waves in a wave.
I know, but I'm just saying that's going to fail because you can't have a half a photon or a quarter of a photon or a quarter of a wave or a little bit of a push.
That's where we disagree. It's like, I think if I do the experiment that, you will be able to get the equivalent of half a photon, but, until I actually do so, then, it's just your word against mine.
Right. I don't think you'll ever get a half a photon, so good luck. But okay, fine. As long as we agree on that's what you're going to... You're going to do the half photon experiment.
That I should be able to hear the difference between a square wave and a sine wave, because they do sound completely different.
Well, obviously...
I don't have an oscilloscope. I can't, see what...
I don't have one either. I don't have one either, but I have worked with them, and I know enough about what they do, is that what they're telling you isn't actually, it's not the real story. They can't show you electricity. They're showing you an abstraction of the electricity. So you can't be always fooled about what it says is happening, because it's making up the difference. It's showing you what the averages would be. It's not showing you necessarily what the individual thing is doing,
Well, I guess that would be a matter of opinion. I would think that...
Well, a trace is a trace. I'm just saying you can't deny a trace is a trace. Once I have it on trace, okay, there's no way it can't fill in all the lines. So it's automatically going to put lines where there doesn't necessarily have to be a line. If I make a voltage that goes immediately from 3 volts to 7 volts, and it went there immediately, it's going to draw a trace. Okay, it's not going to draw an immediate. It's going to draw a line showing a progressively... Well, it went to 5 volts, then it went to 6 volts, and then it went to 7 volts. Well, no, it didn't really do that. It went straight up and then straight back down again, okay? It didn't do any of that line that the trace drew for me.
Well, it'd look pretty vertical, so that would kind of indicate that it didn't spend very much time in
I'm just saying the trace speed will tell you, so the trace speed's never going to be fast enough to get that perfectly vertical line, so it's always going to fill in some lines, and it's going to give you some fake lines where... the pretend voltage of 5 volts, you actually went through it when you never went through 5 volts. I'm just saying that it's just in the nature of the function of a tracing oscilloscope is going to be creating some fake lines. It's like drawing your name without any spaces, with one continuous line or whatever. It's going to be a little different than if you pick up the pen and start over again.
All right. Well, it looks like we're getting here on about 2 hours, so maybe we can kind of summarize about what we were talking about.
Well, so far there's no evidence that anybody can be convinced of anything. So yeah, we didn't make too much progress. I'm a little disappointed, but I didn't have too high expectation. I didn't think it'd hang on the word force, frankly, just because the idea of a field of soldiers wreaking mayhem in the universe seems to me a great analogy, that there's a bunch of little maniac soldiers moving the speed of light flying through the universe, and they're just banging into shit and pushing it around, and that works for me.
Yeah, we get hung up on that word of force, but I'm thinking that is analogous to whatever my sea of particles is. I mean, if I call my little particles your force things, then we would pretty much be in agreement, I would think.
Except mine are always moving and yours are always standing still waiting to be vibrated. So that would be a difference.
Yeah, but they're kind of in a chaotic environment, constantly being jostled about and moving. Similar to...
Well, your force, your field of particles already has energy in it, in the sense that the spots in space already have stuff going in a direction. So there's already plenty of energy in the universe, because there's plenty of these perturbations flying around, going from all of these places. So there's already plenty of energy. So in that sense, it is compatible. So we do have some compatibility there. And as long as we don't get too hung up on forcing each other to comply,
I mean, that's just, the biggest difference was whether you brought the domino thing, which is whether it's one domino going from A to B, or whether there's one domino hitting like blah, 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 all the little dominoes. So we still have that difference. Although we also talked about polarization, and I think we kind of agree that a polarization is bigger than, say, an atom or an electron. It's got some finite width. And we might disagree about how much that is. You say it might be like thousands of atoms.
I'm just saying that you can probably be you can trust me. I hate to say those words. It's the same as with the rest of the electromagnetic spectrum. So you'll find that the length of the perfect antenna is proportional to the wavelength in terms of the measurement. So the antenna length is always the same as the wavelength length. So if there's if the wavelength has a 3 centimeter distance at the speed of light, then the antenna that'll be optimal will also be 3 centimeters. Those two are always proportional.
Yeah, I think that there's no argument there, but I think it's interesting that kind of our polarization ideas kind of line up. That there's something that determines the polarization. You know, it's not what mainstream says, which is
well, mainstream says nothing, right? They say nothing. They don't explain polarization. They don't tell you how long a photon is, and they don't even ever talk about the polarization length.
Well, they say the transverseness is encoded on the electromagnetic
right,
field.
but I'm just saying they never talk about the height of that polarization. They never talk about the height of it.
That wave. I don't know. It's not.
I'm just saying they're telling us that a single electron moving from one energy level to another energy level makes a photon. And my argument is it can't possibly create a whole photon. It has to be a player. It's creating a piece of the photon, but it can't be the whole photon.
Yeah, then we got a little bit into, let's see, what, we did discuss a lot about whether, space is filled with something. You can't really conceive of, space being filled with ordinary matter, like I think it's filled with ordinary matter, neutrons, right? So, I mean, I tried to give some arguments as to say that, it's like, yeah, well, a light wave would be able to travel through that.
Well, why wouldn't gravity consolidate all of the matter in space? So if there's going to be electrons and protons or positrons in space filling it, why wouldn't they all consolidate like they do on Earth and everywhere else?
Well, actually, they do. I mean, I would say that the positive-electron ether is denser here on the Earth. I mean, it's attracted like everything else gravitationally. And that's why clocks slow, because literally the pendulum of the clock has to slog through more particles, and that's why it slows down. So yes, I would say that
pendulum clocks. I don't even know why you're saying pendulum clocks slow down. I don't think there's any evidence that they do.
That's something that's experimentally observed.
Where
clocks on Earth run slower than clocks.
No, that's not true. I mean, sundials don't work at all in space, and lots of things change when you move them. So, I mean, the only thing we're talking about is atomic clocks. Atomic clocks.
Yeah.
Okay, and that has to do with decay. So decay is a whole other subject, which we didn't get to, because I would argue that decay. They say like a muon decays. Well, it doesn't really decay; it just slows down. So
yeah,
slowing down
into that whole relativity thing, thank God. But you brought it up that if there is a normal matter ether, that it should be concentrated around the Earth.
Well, we would agree that clocks are broken, and you're not changing time. You're just breaking clocks. Clocks don't work.
Yeah,
if you put a clock you put a clock in a bucket of water, it sometimes doesn't work. Okay, so
But I don't think I've convinced you that space is filled with normal matter.
You'll never convince me that space is anything other than a vacuum. Okay, and that's it. And yeah, that's.
Well, your vacuum is still filled with your force particles. So
of course. Yeah, like I said, yeah, it's not I mean, theoretically, maybe you could get all the force bits not to exist in a piece of it, in one jar of space, but I'm just saying that, yes, theoretically, space is full of cosmic background type radiation. I mean, there's a ton of radiation hitting us all the time, little bits of energy. All the time.
Well, I don't know. Then maybe we're just splitting hairs here, because your force particles are some kind. I mean, they're not normal matter, but I'm just saying that they are. So.
Well, I'm just saying they're the cause of momentum. The matter is dead, and it needs the force to act. So I'm just saying that that's the actor is the force. Now, obviously, that's the same thing. You're saying the movement of the matter in the ether, okay, the perturbations, whatever you want to call them, those vibrations in the matter are what's going to move the piece of matter that's the consolidated matter. I'm just saying, to me, it's easier to just think of the consolidated matter as matter, and then empty field. This guy's just got the perturbators in it. It's just got the the force. So again, we're just back to the domino scenario, right? I mean, it is compatible if we can both agree there's boot at this end and there's boot at this end. And that's really all that happens, right? I mean, force comes off of something and it's transmitted to point B, where it boots a piece of matter that we call matter, you know, one that we call an earth or a billiard ball or some other piece of matter. So, you know, who cares what's in between the two boots? So in that sense, I think we can agree.
Although I care, but
I'm saying who cares for the sake of argument if we can't resolve that one. I mean, I'm not going to come up with any proof of, you know, the absence of your God, and you can't prove that my God doesn't exist. So we're stuck with a model where neither one of us can prove there's no dominoes. I can't prove there's no dominoes. You can't prove there is dominoes.
Well, I'm hoping that, say, the University of Washington next door to me, I'll convince them of my theory, and then they'll do some experiment that actually pulls out all the positrons and electrons, and they measure density or something like that, and it becomes clear experimentally that...
I just don't know how they still don't have mass right now. Why don't they have mass right now? If I take a jar of empty space and I put it on a scale, it's got no mass. There's no mass in there.
No, it might have mass. It might have the mass of 1,000,000 times denser than steel. It's just it's surrounded by all this other denser than steel stuff, and so it's
well, I'm just saying it doesn't have what we know of as normal mass. We can measure an electron, and you're saying that somehow these electrons, if I put the space electrons in a jar and I bring them back to Earth, somehow they don't weigh the same much as
Well, the thing is that in order to weigh something, it has to actually, there has to be a container, and there's no way that you can contain these things. They're like neutrons, and neutrons slip through everything. So how are you going to weigh something that just...
Well, I don't believe that. I don't believe that for a minute. I don't think neutrons slip through anything, but you know, electrons and protons certainly don't slip through anything.
Well, that's something you might want to look in electrons, because neutrons, when they come out, they can go through like 5 feet worth of cement. They interact.
Well, I know that's what conventional physics tells us that happens to things, but I'm just saying I would doubt whether they can even measure a frickin' neutron and tell the difference between that and, you know, in many cases an ion. So I'd have to see the experiment.
Well, that's something you might want to take a look at, because we agree that, you know, when it comes to questions like this, we should look at the actual experiments. And, you know, maybe we don't believe the experiments, but if we see the experiment and, you know, say you find some convincing evidence that, say, that's interesting that you don't think the positron exists. But, you know, if you did some research and you look at it and you say, oh, well, maybe it does exist, because, you know, they could do X, Y, Z. I don't know. But
well, look, even when they name that name that device that shoots, you know, that's supposed to shoot them, you know, positron something radiation, you know, where they do a medical treatment and they call it positron something magnetic radiation or something.
Yeah,
and the irony is there's no positrons. It's the same as all radioactive therapies, and they're saying the positrons happen inside the body, where the radioactive isotope you injected in the person emits a positron, and then that creates a photon that they see. So the irony is the positrons aren't really in the experiment; they're just the theoretical part. You know, there aren't any. They don't actually shoot the positron.
These are hard science things that we can look into.
Well, I'm just saying, hard science. You know, you're using these words when every single one of these extraordinary neutrinos, all of these particles have been just declared to exist by CERN based on, and you know it. They don't have any photos of a quark. They don't have any photos of any of this crap. These are things that last 1/100th of a millisecond in their experiments. I mean, this is such weak evidence of something's reality. And what is the role to play? I just mean we can agree. I don't care whether you call it a positron or a proton. We can agree there's two equal charges in the universe. There's the negative elements and the positive elements. If we can agree on that, we're sort of safe. Right? I don't care whether you call them positrons.
No, I would say that the proton is made out of 2 positrons and 1 electron. So there's a definite difference there.
Right. I'm saying that's okay. If you want to do that, it's okay with me. But then you'd end up, in my opinion, okay, then you're talking about this weird 1/3 charge and, you know, or 2/3 charge.
1/3 charge. I mean,
well, I'm just saying.
2 positrons and 1 electron. See, I don't use all that partial quark stuff. That's a bunch of hooey.
I understand, but the shape of the thing is still going to be difficult because then all protons can't be alike because there could be where are these electrons and positrons inside of the proton. It's always going to be a geometry. I'm always going to try to break it down to a geometry. They have to have a place in space, so they can't just mix with each other like you're mixing paint colors and you just make purple or something. It's got they do have to have a shape of some kind. Well, anyway, I won't get into all that. I'm just saying, for the sake of argument, all we have to understand is there's a concept of charge where there's north-south, the two ends of the magnet, and there's an equal. I'm just saying that we know from magnets that the charge, the force, is equal. That the south pole is just as strong as the north pole in theory, and that the positive charge in the universe has to be sort of balanced with the negative charge in the universe.
Well, I mean, we agree on that, but what I'm trying to bring out is a difference that you don't believe a positron is any different than a proton. So that's a major difference between the two of us. So we discussed that, and then we got a little bit into what gravity is, and I understand your gravity is sort of like a pushing, let's say, kind of gravity where everything just pushes on each other.
It's really not, in the sense that I'm saying it's a thermal equilibrium problem. The Earth actually has matter in it. The matter moves. To move, it used up force. It used a little bit of the force's energy because the force was going from point A to point B at the speed of light, and when it had to push an electron, it didn't move as fast, so now it got slowed down a little, so it lost a little bit of its momentum. So there's a net momentum loss when electrons and protons move, and that creates gravity. So more energy goes into the Earth than energy coming out of the Earth. Because
I was curious, does that apply to small masses?
It applies to electrons and protons, yes.
Individual electrons and protons. I mean, if I have a block of concrete, another block of concrete, I mean, does the gravitational force work between the two blocks of concrete?
They both have they're independent. They don't need each other to show up. The gravity of the Earth already exists long before an asteroid shows up. It doesn't need to have any. There's no contributing. Everything creates its own gravity, and the gravity is I've used up a little bit of force. Okay, so me just existing with matter in me, condensed matter, means more energy comes into me and a little bit less comes out. And now I'm all of a sudden attractive because obviously if I'm facing you, I'm giving you a smaller dose of the universe than the rest of the universe is, right? So when you look at me, there's actually less energy coming off of me than would be coming from the plane universe, and therefore you're going to be attracted to me.
Okay, so it would work with small bodies like humans and blocks.
Oh yeah, no, it goes all the way down. It's a nuclear force. It really just affects electrons and protons. It doesn't. They're the only thing that move in the universe. Everything else is.
Okay. We discussed a little bit about that, and we discussed a little bit about, you brought up the point about, well, if there's this electric charge field, where is it? And it's like, yeah, you can measure it. So that might be something you want to look into, which is that there is a measurable electric field. We're sitting in a very big electric field, actually.
Well, we'll have an arguing. We're arguing about mediums, and yes, there's voltages inside of wires. So yes, I can go this far up the wire,
like say thunderstorms and stuff.
Well, yeah, I'm saying but that's just electrical potential. Of course, a medium will create an electrical potential, but the electrical potential is not a real potential. That's just because the fact is we are a conductor. We're living in a conductor.
Let's see, what else did we discuss? So we discussed gravity a little bit, and then where did we go after gravity?
Well, we did photons. Well, we're getting there. We sort of agree there's these four elements, right? There's gravity, magnetism, electricity, and light, right?
I think we discussed a little bit about magnetism, about how, I was bringing up that, theoretically, a charge not in motion is not affected by a magnetic field. Now, I actually don't have any personal firsthand, experience with that, as in I can't observe a single electron around a magnetic field and show that it's not moving. I only know that by the Lorentz force law. But yeah, well, I kind of believe that. So, and my theories kind of explain that. Why is it a particle not in motion does not move?
Well, I'm just saying the two fields are it's one field, it's magnetism, and the only thing is that magnets are always conductors, and the fact is you can charge their surfaces, and if you charge the surface of the magnet, you break its magnetism. You completely destroy it. So magnets start to dysfunction when you charge them. So, but when you put a magnetic field that's stronger than the thing you're moving, the electron, much stronger, the electron will not affect the magnetic field, and obviously the magnetic field will repel. The north end of the magnet will always repel the electron. The south end will always repel protons. And that's how we move them around, actually. That's how we manipulate them, is to create those very fields. But anyway.
Okay, yeah, I think that was pretty much what we covered. I think we actually ran way around the field. I think we actually got a pretty good kind of overview of a lot of different things because I was especially interested in the areas that we kind of differ. And to our viewing audience, so hopefully we made that clear.
And maybe I can persuade Franklin to make maybe a 20-minute video on one of these subjects, and then I'll respond to those specific points if he has specific evidence and wants to make a more specific argument. And again, I think we should try this again and see if we can get any further.
I thought it was a very good collegiate, positive discussion. A lot of people were afraid that that they accuse you of not being able to argue with you without you swearing and stuff like that. But no, you didn't do anything like that. I thought you were quite reasonable.
Yeah, I'm really a nice guy. It's just obviously you get a few haters in the world and they call you all kinds of bad things. It's just what they do. They just want to make me into some kind of monster, horrible person. And I'm really nice.
But I think generally, we kind of agree. Maybe we kind of look at things kind of differently. Like you see little force particles, I see actual positrons, electrons. But fundamentally, there's something in space other than nothing. So I think we both agree, as opposed to mainstream who think that there's nothing in.
Well, they think there's 400 fields. Okay, they think there's 400 magical, different whatever pathways of communication. Electrons have their own field, and protons have their own field, and positrons have their, and then all the antiparticles, and all the muons, and the taus, and the this and that, and they all have their own field. I mean, it's that ridiculous. They have their own personal chauffeurs that, virtual photons that transmit either the signal to come towards me or move away from me. It's like a taxi has to deliver the message that says, move away, here you are, move towards. It's not,
Yeah, I think during our discussion, you brought up some interesting analogies, like they're getting closer and they're further away. And
yes, it's a good one. That's a good one. I thought of that a couple of months ago, and that's just, to me, it's really good at explaining how you create what you would call a wave. In the sense that I'm creating a high density of photons, and then I'm creating a low density of photons, and a high density and a low density, just by moving back and forth.
Yeah, it's definitely some high low density in something, but okay. So like I said, we've gone over our 2 hours,
yep.
And I think we got some things to think about. So I don't know, maybe if you want me to do a specific, because I find it hard to motivate myself unless someone is challenging me with something. So if you want me to make a 20-minute video, just say, Franklin, why is it you think that this is that? And then I'll do it.
Right.
I'm not going to do it on my own.
All right, well, do the length of a photon. The photon, in my opinion, is a timed event. You have to produce one over a period of time. You have to receive one over a period of time because it has a frequency. So how many waves are in your photon?
I don't know, the shape of the photon. Maybe I want to do a video on that, because I think that that was the invention of the DNA structure. There's a structure to that photon, and someone's got to figure it out. And when they do, they'll see that that this is how that all comes together.
Well, just to include the pieces. Include the pieces. The height, the length, okay, and then the idea that it has to land on a surface and cause electricity.
Yeah, okay. Well, maybe I'll think about that.
Okay.
All right. So, but I think that does it for this discussion. Very interesting. I thought profitable.
All right. So
it was interesting to talk with someone with different ideas, or to challenge my own ideas. So. It's all good.
All right, well, I'll close the public, and then, for the rest of these bums, and then me and you can talk all kinds of secret plots and plans and whatnot. So we'll call this a success, and till the next time, and such.
Yep. Until the next time.
And
So if you
such.
have any comments, send them to, say, franklinwho@yahoo.com, or go to my website. I've got all my papers.
I'll leave links
Very
below.
easy.
Links to his website and his YouTube channel will be in the description of the video.
And nobody writes me, so I'm very disappointed. I keep on expecting the Nobel Prize Committee to come breaking down my door, but they never do.
Well, I'm
So,
gonna break down theirs eventually, but whatever. Okay. All right. So till the next time and such.